All right, let's we hopefully you've looked at derive the period for the formula of a period of a pendulum, which is a little bit tricky, and you don't need to know how to derive that, but just thought you should see where the basic formula comes from. The maths for pendulums actually is very complicated, but we try and keep it all simple. So we've got a spring, and we've got a spring bouncing up and down, and we want to know its period. Remember, period's always from one point to another. So if you start there, it's the trip down to the bottom and back up to the top, always the same. Now, we found it was interesting to look at the forces. Now, force equals mass times acceleration, but the force we know on a spring, that's the equilibrium point. The force is proportional to the distance. So again, I'll use y again. Force is equal to ky, or kx, doesn't really matter which one we use. I'll use y this time. So we can equate those and say, well, ky equals ma, and we can say then a equals ky over m, right? But we know that a equals omega squared y, dropped off the negative there, so we can say omega squared y equals ky over m, getting rid of the y's again, that's nice. And we're almost already there. The spring one actually is a lot easier than the pendulum one. So we can say that omega equals 2 pi over the period. So omega squared is equal to 4 pi squared over t squared. So 4 pi squared over t squared is equal to k over m. So we rearrange that, and we want the t up the top there. So t squared can go back up there. T squared is, and we've got the 4 pi squared stays up there. We bring the m up, and we bring the k back down. And so we take the square root of both sides, and we've got t equals to 2 pi square root of m over k. If the mass gets bigger, do we expect the period to get bigger? Yes. If the spring constant gets bigger, do we expect the period to get smaller? Yes. So this all seems to work. Well done us.